Good morning.
Morning,
Okay,
ma'am.
Morning, ma'am.
so last time we have um, derived the integral form of Gauss law, and then we also have derived the differential form of Gauss law. So if you can recall, we have Gauss law in integral form is you have this one, E dot dA is equal to Q enclosed over epsilon naught. And we have the differential form of Gauss law. So we have the divergence of the electric field is equal to rho over epsilon naught. Okay. Now, uh, let us derive this form of Gauss law from directly from this familiar equation. So we have this equation E as a function of r is equal to 1 over 4 pi epsilon naught integral over the volume. We have rho, asa ganin ni siya nga equation class? Atong continuous nga distribution. Okay. Okay. So from here, we will derive, from this equation, we will derive the differential form of Gauss law. Okay. Take note that in the previous discussion, we have derived this from asa ganito katong electric field of a point charge. This time we will derive the differential form of Gauss law from this equation, which is so ganun siya, electric field of a continuous distribution, volume distribution of charge. Okay, so from that equation, we can get the divergence of the electric field, which is equal to 1 over 4 pi epsilon naught integral of, so let us just get the divergence of E. So your electric field is equal to 1 over 4 pi epsilon naught rho over r squared r hat. So we have here r hat over r squared, and then we have rho r as a function of r, and then we have d tau. Okay, so this is from kini siya nga equation. Let us just call this equation 1. So from equation 1, kuan lang na to ang divergence. Okay? So gi-switch lang na to ang position sa r hat and the charge density, the volume charge density rho, such that sayon siya nato kuan og divergence, since in our previous example we have already obtained the divergence of 1 over r squared r hat. If you can recall, the divergence, recall that the divergence of, who can recall class, the divergence of 1 over squared r hat. So this is equal to, so this is from previous example. So this is equal to 4 pi multiplied by the Dirac delta function, which is in 3 dimension, where again, your r, the separation vector, is equal to r minus r prime. Okay, so the divergence of the electric field can be rewritten as 1 over 4 pi epsilon naught. And then we have here inside the integral, we will just substitute this into this. So we have 4 pi multiplied by the Dirac delta function, r minus r prime, and then we have our rho d tau. Okay, now we can take this out of the integral sign, right? Since this is constant and it can be cancelled out with 1 over 4 pi here. And then take note that, sa ganito, the Dirac delta function has values of either 0 or 1. So, if r is equal to r prime, then the integral of the Dirac delta function is equal to 1. Therefore, ano sa'yo nabilin class? We have rho over epsilon naught. So we have here the divergence of E is equal to rho over epsilon naught, which is exactly the same as the differential form of Gauss' law. Okay? All right. Now this time, we will have some applications of Gauss' law. By the way, class, kini si Gauss' law is the quickest and easiest way to calculate electric fields. But take note that we can only use Gauss' law if we have a symmetric system. So if symmetry permits, we will be able to use Gauss' law. So ang technique lang is, for example, if we have a system and then, for example, it is a wire. So infinite wire, for example. So since I think this has cylindrical symmetry, so we will be using, for this particular system, we will be using a cylindrical Gaussian surface. And for example, if we have a point, we can use a spherical Gaussian surface. Or if we
Mhm.
have a
Ma'am,
sphere, yes?
I have a question about the last page.
Yes, yes, yes.
Wait. If R is equal to R prime, di ba mag-zero?
Ah, yeah, yeah. So, sige to. So, if you have a Dirac delta function, we have, this is x minus 1, then at x equals 1, nadira ang peak. So, dira ang 1, okay? So, at r equals r prime, muto siya ang na-evalue nga. Your Dirac delta function will be equal to 1 at x equals 1. I guess. Take a look. Kindly take a look at your notes. Sakto ba? Other points aside from 1, kay ma-zero na siya. If mo to siya. Yeah. Can you confirm? Okay, sakto siya. So at r is equal to r prime, that is where the peak is. So at that point, the integral of your Dirac delta function is equal to 1. Okay ra, kinsa to nangutana si Julius? Okay ra?
Yes, ma'am. Pero if R is equal to R prime, sa kani ma'am ba, sa kaning divergence of electric field, nganong mabilin ang rho, tas ma mabilin ang rho, and then over epsilon naught. If zero na siya, ma'am.
If 0, what do you mean?
Ang
Ah,
R
okay.
minus R prime,
So at this point, your r prime here is a constant. So constant ni siya. We can actually take this out of the integral. This one, 0. And then ato lang integrate is the Dirac delta function. And then we have here d tau. So three-dimensional Dirac delta times we have d tau. So if we get the integral of that, that is equal to 1 at r is equal to r prime. So what is left is
mazero ang
1 over
r.
epsilon. Yes?
Dili mazero ang r minus r prime, ma'am.
Ay,
1 siya.
dili ni siya kuan ha. This is the Dirac delta function as a function of r minus r prime. Dili siya mura ni siya ingani Julius. F of x as a function of x.
Sige ma'am. Get. Ay ma'am, pwede i-list ng color sa ano ma'am sa kanang napasulat
sorry.
niyo ma'am.
So,
Ay medyo sa mata.
okay, sorry. All right. So mura siya variable or mura siya f as a function of x or the Dirac delta function as a function of r minus r prime. Okay ra? So dili ni siya multiplied by the Dirac delta d cube multiplied by r minus r prime. So mura siya as a function of. Okay?
Okay,
Klaro
ma'am.
ba? All right. So again, if you have charge distribution or spherical nga charge distribution, then this has, or you can use a spherical Gaussian surface since it has a spherical symmetry. And then if you have a plane, for example, so kung plane, what we'll be using is a Gaussian pillbox. So you have here mura siya og box. Mura siya box class wherein you will be enclosing some parts of the plane. Okay? So we can only use Gauss law if symmetry permits. So for example, we have here a problem. Example. Find the field outside a uniformly charged solid sphere of radius r. And total charge q. So our system here is a uniformly charged solid sphere with radius r. Okay, so for this problem, we can use, of course, our approach to this problem class is first we have to draw a spherical Gaussian surface. Since we are asked to find the field outside a uniformly charged solid sphere of radius r, then this spherical Gaussian surface should have a radius greater than that of r. So draw a spherical Gaussian surface with, say for example, radius r, gamay nga r, which is greater compared to big R. Okay, so say for example, this is our Gaussian surface. Again, it has a uniform charge distribution. It is uniformly charged, and then it has a total charge of Q. So na siya total charge Q. And then our Gaussian surface should have a radius which is greater than r. So if this is this sphere, small sphere here, has a radius equal to big R, Then this one, our Gaussian surface should have radius r which is greater than big R. Okay, so according to Gauss law, uh, so most of the time class, we will be using the integral form of Gauss law since it encompasses or pwede ta mo gamit og line charge, pwede ta mo gamit og surface charge and volume charge. Okay? So we have E dot dA is equal to Q enclosed over epsilon naught. So for this example, our Q enclosed, what is our Q enclosed class? Q enclosed is equal to Q. Okay, so the enclosed charge is just equal to the total charge of the sphere, which is equal to Q. Now take note that for this, the electric field is ahagani padulong ang electric field class. So diri siya no. It is emanating radially outward from the sphere. Okay. Now take note that for this, it is emanating radially outward. The electric field is emanating radially outward. And take note also that for our spherical Gaussian surface, kung magkuha kog small infinitesimal area here, dA, your dA is directed perpendicular to the surface. So, diri siya padulong. Now, notice that your electric field, which is due to the solid sphere, is parallel to the direction of the infinitesimal area. Okay? So, parallel ang iyaang direction sa infinitesimal area. Therefore, the magnitude of E is constant over the Gaussian surface. So, because of that, the magnitude of the electric field is constant over the Gaussian surface. Over the Gaussian surface. Okay. So we can take E out from the integral and then we are only to evaluate dA. But we know already what is the integral of dA for a spherical surface. Sa ganito class, ato na lang i-integrate siya. So we have for this, wherein our R is constant, atong R is constant, we have R squared sine theta d theta d phi, or kabalo naman tada class no? We have R squared sine theta d theta d phi equals Q enclosed over epsilon naught. So we have E, sorry for this. This is the magnitude of E. We know that this is equal to 4 pi R squared. Okay. 4 pi R squared, since sine theta d integral of sine theta d theta is negative cosine theta integrated from 0 to pi, and then we have d phi, integral of d phi is phi, which is integrated from 0 to 2 pi. So we have 4 pi R squared. So we have here your R squared. This is equal to Q enclosed over epsilon naught. So the magnitude of your electric field is equal to we know already that the Q enclosed is just equal to Q, the total charge of the sphere. So we have here E is equal to Q over 4 pi R squared epsilon naught. Or we can rewrite this. So the electric field vector is equal to 1 over 4 pi epsilon naught Q over R squared, and it is radial So it is directed radially outward. All right. So notice that the field outside the sphere is exactly the same as it would have been if all the charge had been concentrated at the origin. So mura lang siya og sa point charge class. So the same lang siya sa point charge. So again, kung nakay ingani spherical with total charge Q, spherical surface or nakay solid sphere with total charge Q, the same lang yung electric field kung nakay point charge with charge Q. Okay. Any questions? Now take note, class, that Gauss' law is always true. But it is not always useful. Okay. So it can only be applied if it can only be applied. So the first condition is if the charge density is uniform. So if the charge is uniformly distributed over the volume, the line, or the surface, then we can use Gauss' law. And if the system is symmetric. Okay? So these are some of the symmetry that works. So for us to use Gauss' law, so these are just the symmetry or symmetric cases that work. So we have the first one is spherical symmetry. So if the system can have spherical symmetry like that of a concentric sphere. So kaganina, we can call this concentric spheres since ang imo ang solid sphere o ang imo ang Gaussian spherical surface has the same center. So the same center, concentric. And then another is if it has cylindrical symmetry or it has planar symmetry. Okay, so for cylindrical symmetry, so for example, pwede ka maghimo og coaxial nga cylinder, parehag axis nga cylinder. And then for plane, you can use a Gaussian pillbox. Okay, so for example, kaganina we have the spherical symmetry. So not a system with spherical symmetry. For this example, example number 2, we will have a system with cylindrical symmetry. So for example, we have a long cylinder. Our system is a long cylinder carrying a charge density that is proportional to the distance from the axis. So that is rho is equal to Ks prime for some constant K. So find the electric field inside the cylinder. So find the electric field inside the cylinder. All right. So we are not given with the length, the dimension of the long cylinder. So ang iyan lang giingon is that it has a charge density equal to Ks prime, where K is constant. And we are asked to find the electric field inside. So what we'll be doing is we should draw a cylindrical Gaussian surface inside the cylinder. Okay, now take note that this cylindrical Gaussian surface should be coaxial. Coaxial. Meaning parehas sa lag-axis sa imuang cylinder, sa imuang system. So if this is the z-axis, wala ko calculate. Okay. So if this is along the z-axis, then your Gaussian surface should be centered along the z-axis. Okay. So suppose your Gaussian cylinder has length equal to L. So yung length equal to L. And then it has a radius of S equal to S. Equal to S. So na siya radius equal to S. Radius of the cylinder, the Gaussian cylinder is S. And then it has a length equal to L. Length. Okay. So we then apply Gauss' law, which states that E dot dA is equal to Q enclosed over epsilon naught. All right. So again, we are not given with the total charge of the cylinder, but we are given with the volume charge density of this long cylinder. Okay, take note that this is your Gaussian surface, Gaussian cylinder, Gaussian cylindrical surface. Okay, now for this, take note that kung nakay cylinder or kung nakay charge nga cylinder, ang imong electric field, ang yung electric field class is radially, or it is going away, or it is directed away from the cylinder. So, ingani iyang electric field. Okay, so the electric field vector is away from the cylinder. All right. Now, we can get Q enclosed. So, pwede na to kwaon si Q enclosed. We have Q enclosed is equal to, we are not given with Q enclosed, but gitagaan tag rho, so we can integrate this. We have rho d tau. Rho d tau. So this is equal to the integral of Ks prime. And then your d tau in cylindrical coordinate. So itong d tau class? Kung cylindrical? Anyone? Pellerin? What is d tau for a cylindrical coordinate system? Anyone, class?
RD phi dz, ma'am.
Okay, very good. So we have R, dr, d phi, d theta. Since z is, sorry, r dr, d phi dz. R dr d phi dz. So we have here, since we are using S, so we have S, ds, S prime, ds prime, d phi dz. Okay, very good. And then we know that P is from, so recall that phi is from 0 to, for cylindrical, P is from 0 to 2 pi. And then we have z. How about z? So z should be integrated from 0 to L, the imong Gaussian. And then your S prime should be integrated from 0 to S. Okay. So dapat ma-master ni siya ninyo kasa. Take note nga ang imong limit is imong tan-awon kay ang Gaussian. So balik sa sphere kaganina, ang atong limit is from 0 to R, nag-integrate ta over the surface. So your Gaussian surface, your Gaussian spherical surface has a radius equal to small r. That is why na-retain na ning ato ang r diri So we have this one, 4 pi r squared. R squared atong gamit. And then here sa ato ang cylindrical nga Gaussian, which is inside the ato ang system, the charge system, ang atong limit, take note that your z is from 0 to L, which is the length of your Gaussian surface. And then your S prime or your Z, kini siya. Your R, the radius. Your S prime is from 0 to S, where S is the radius of your Gaussian cylinder. Okay, take note of this. So we will now evaluate this one. So what we get is, so we have Q enclosed is equal to K. We can take K out of the integrals. We have 0 to S, S prime squared, ds prime. And then integral of d phi from 0 to 2 pi. And then integral of dz from 0 to L. Okay, so we have our Q enclosed is equal to 2 pi k. So this is 2 pi, then k. And then we have L here. And then here, this is s squared ds. Integral of s squared ds is equal to 1/3 s cubed. Okay, so this is our Q enclosed. Okay, so since E is pointing radially outward, so kining imong curved portion class, sa imong curved nga portion, this is your curved portion, kining body sa imong cylinder. Sa body sa imong cylinder, your dA is also padulong dito kung diri ka magkuhag surface, then your dA is also padulong diri. So it is parallel with the electric field. Okay? Whereas diri sa imo ang bases, sa imong mga bases diri, ang imo ang dA is perpendicular to the electric field. Therefore, kining duha ka bases sa imong cylinder kay wala siya contribution sa imong total nga electric field. Ito ba? Or wala kay flux diri zero ang flux diri sa mga bases. Okay? Kaya ano ganito, ang imong electric field padulong dito, radially ang direction, which is perpendicular to dA. Imo ang area vector is perpendicular with your electric field. Okay? That is why zero ang imong flux diri Okay, so ang ato lang i-consider is kining sa body, sa imong cylinder. So for that, we have integral, so body. So integral of E dot dA is equal to EDA lang no, kay kuan naman siya kanang parallel. Now, your dA, sa body sa imong cylinder, what is your dA? Dapat ma-master ni siya ninyong class ha. What is your dA sa body sa imong cylinder? So, kung magkuha ako diri og, for example, this is our Gaussian cylinder. Kung magkuha kong surface diri sa body, gamay nga surface, unsa may dimension ani niya? So, this one is dz. This one is, kini siya, nga length is S d phi. Okay. S prime d phi. So our dA is equal to S d phi, S prime d phi dz. Where our S is constant. So S prime is equal to S sa tong Gaussian surface. Okay? So constant siya diri sa surface. All right. So we have here E integral of S na akong ibutang class ha. Substitute na nako si S prime with S. And then I can actually take this out of the integral. Sorry. So we have integral of d phi from 0 to 2 pi. And then your z is from 0 to L. Okay, so this is equal to Q enclosed. Your Q enclosed is, ano ito? 2 pi KL, or 2/3, this one class, 2/3 pi KLS cube. Okay, over epsilon naught. Okay, and then we can further simplify this one. So this one, kini siya is 2 pi L. So naakay, in the left-hand side of your equation, you have E, 2 pi, sige ito. You have 2 pi LS or SL. 2 pi SL is equal to your Q enclosed equals 2/3. Let me just 2/3 pi KLS cube. 2/3 pi KLS cube divided by epsilon naught. Okay, so your electric field is equal to, you have 2/3 pi KLS cube divided by 2 pi SL epsilon naught. So we can cancel this. We can also cancel this one. We can cancel L. And then we have this one is squared, canceled. So E is equal to K S squared over 3 epsilon naught. Sakto ba? Okay. Or, para tsada siya lang tawon, we have the electric field is equal to 1 over 3 epsilon naught. You have Ks squared. Okay? 1 over 3 epsilon naught Ks squared, and ang iyang direction is along the S prime. So, radial iyang direction. Alright? Any questions, class?
None, ma'am.
Alright. So, I think I have here another example. So, for our last example for today, we have an infinite plane carrying a uniform surface charge sigma. So, find its electric field. So, we have here a plane. Suppose this is your plane. And then it has a uniform surface charge density sigma, uniformly distributed over the surface. So we have to find the electric field. So for this, we will be using a Gaussian pillbox as our Gaussian surface. Okay, so magdraw tag box diri Suppose this is your box, class. Box. Mura siya box. Okay. Suppose this is your box nga na-enclose niya ang some part of your plane. Okay, murag na sa iyang tunga sa imong box na dito imong plane. All right. And then we'll be applying Gauss law. So we have the integral of E dot dA is equal to Q enclosed over epsilon naught. And then here, what is our Q enclosed, class? Q enclosed is just sigma multiplied by the area, the total area. So say for example, the area of the plane, the area of isa ka side sa imo ang Gaussian pillbox is A. So we have your Q enclosed is equal to sigma multiplied by A. So again, kining A diri a class, this is the area of the top and bottom of your Gaussian pillbox. So nganong top ug bottom naman natong gi-consider since for this plane, ang imo ang electric field is perpendicular to the plane. So, electric field is padulong dito or pwede pa siya padulong sa ubos. So, kining mga kining nga side sa imong pillbox, kining nga side, kining diri nga side, diri og diri kay wala siya flux. Okay? Nakuha ninyo, class?
Yes, ma'am.
Okay. So, by symmetry, E points away from the plane. So, it is pointing away from the plane. Thus, only the top and the bottom surfaces of the pillbox yield. So, if A is the area of the lid, so kini, the lid, kini siya, or kining sa ubos, then, your E dot dA is equal to E multiplied by 2A. So this is equal to Q enclosed over epsilon naught. But we know what is Q enclosed. Our Q enclosed is equal to sigma multiplied by A. So we have here E multiplied by 2A is equal to sigma A over epsilon naught. Okay. Therefore, our electric field is equal to sigma A divided by 2A epsilon naught. So it is not actually dependent on the area of the lid of your pillbox. So your electric field is equal to sigma over 2 epsilon naught. Now, if you have recalled, or if you can recall, nakuha ni siya na to nga electric field for an infinite plane. Sakto ba? So we have an example in our previous example, we have a long solution in order to get the electric field for an infinite plane of charge with uniform surface charge density. So kini using Gauss law, pila ra ka lines? Less than mga 5 lang ka lines. Okay? So this is now the electric field vector. So we have sigma over 2 epsilon naught. We have here n hat. So n hat is directed perpendicular to the plane. So this is much easier compared to our previous example. Tanawa ganin ninyo ang solution ato last time. Ato ang solution ato last time, class. The example man ako last time, infinite plane. Okay. So for your okay. Maghatag ako assignment later, class. But we have another example. Last na ni siya nga example, class. Okay. So take note, class. If you can recall So the electric field of a sphere falls off like 1 over r squared, right? So mag-diminish ang electric field sa sphere by 1 over r squared. And then for an infinite line, it falls like 1 over r. So the electric field for or of a sphere falls off by 1 over r squared. The electric field of a line, infinite line, falls off by 1 over r. But if you can notice, the electric field for a plane, an infinite plane, does not fall off at all. So you have this one. So it is not dependent on the area or di siya dependent sa distance. Okay? Now for our example, we have here duha ka plane that are parallel to each other. So this plane are facing each other. So ma-imagine siya ninyo, kas. So two infinite parallel planes carry equal but opposite uniform charge densities. So say for example, this is positively charged. So yang charge density is sigma, uniformly distributed over the plane. And then the other one is negative sigma. Okay. So we are asked to find the field in each of the three regions. So asa man nga region? So sa left sa imo ang positive nga sphere, positive nga plane. So this is region 1. And then between the plates, this is our region 2. And then to the right of the negative plate, this is our region 3. Okay. So in our previous example class, we know that the electric field of a single plate is equal to 1/2 sigma over epsilon naught or sigma over 2 epsilon naught. Okay, so let us see kung unsay electric field diri, ug diri. All right. Now take note that the positive plate produces electric field that is equal to this one but is pointing away from it. Okay, so for example, mo ni siya ang side view sa imo ang plane. Sa imong plate. Okay. So if this is your positively charged plate, then ang iyang electric field is pointing away from it. So this is the electric field pointing away from it. So diri pagawa siya. And then if na po kay negatively charged nga plate, ang iyaang electric field is pointing into it. So this is the electric field of the positive charge plate. Take note nga di siya mag-fall off. So the same lagi po ng electric field strength niya diri pareha ba siya kataas. And then for this into no. So this is the electric field of the negative plate, electric field of the negative plate, and then kung diri po ka maglantaw na po kay ngani nga vector, electric field vector due to this negatively charged plate. Okay. So here you can see nga sa region 1 mag-cancel out ang take note nga para sa charge density equal ang ilang charge density. And bahalag unsa pa ni kadako ning imong plate 1 compared to plate 2, dili magmatter ang area, no? So we have here, we can see nga mag-cancel out ang electric fields due to the positive plate and the negative plate sa area 1, sa region 1. So region 1, region I. So the electric field is equal to 0. The same with region 3. So mag-cancel out ang electric field due to the positive plate and the electric field due to the negative plate also. Pareha man siya magnitude pero opposite lang of direction. So region 2, patakabalo, region 3, the electric field is equal to 0. Now here at region 2, we have kini siya, ang sagari ni siya class, 1/2 sigma over epsilon naught. And then this one also has magnitude 1/2 sigma over epsilon naught. Therefore, at region 3, at region 2, the electric field is equal to So at region 2, mag-add up lang sila, no? Na kay 1/2 sigma over epsilon naught plus 1/2 sigma over epsilon naught. So this is equal to sigma over epsilon naught. So between the plates, the electric field is equal to sigma over epsilon naught. Okay? So this will be all for today. Do you have any questions, class?
Wala, ma'am.
Okay. So thank you so much for coming, and then I will see you next meeting.
Thank you, ma'am.
Sige.